Hello everybody, welcome back. So welcome to our first video showing a concrete example of an Excel model for a two-stage stochastic optimization problem. I created a video that goes over the key concepts that you need to be able to understand what's going on when you introduce this type of uncertainty into an optimization model. If you have not watched that conceptual video yet, I highly recommend that you go there first before you do this one, because in my experience, this one is much easier to understand and follow if you see that one first. So I'm going to leave a link to that other video in the description of this video, and I'm also going to add a link to it up here up top that you can click to go there right now. So pause this one, go watch that, and then come back. So just to recap a little bit of the concepts, the idea is that certain problems consist of two stages: a decision I have to make today and what I'm calling the tomorrow. You can think of that tomorrow in quotes, or the near future, which is some uncertainty that is going to be revealed to you. You don't know about it yet, but you can sort of have an idea of what can potentially happen to you by thinking of it in terms of scenarios. So I want to make the best decision possible today, considering that my tomorrow or my near future could be one of several discrete situations. And for each of these situations, I may have some data, and I also have some likelihood of them happening. And the example I gave in the other video was, let's say I'm a farmer. I want to decide what to plant today, given that my tomorrow weather could be, dry, average, or wet. So what is the best decision today, considering these possible tomorrows? So the steps for a problem like this are: determine which are today's decisions and which are tomorrow's decisions. So stage one is today, stage two is tomorrow or the near future. And once you enumerate these tomorrows, you also figure out, what their chances are, or this could be also given to you in the problem. Then you're going to make both your variables for stage one decisions and stage two decisions. And because there are many stage twos, you're going to have many of these variables, one set per scenario in stage two. And likewise, you need to create constraints. You're going to have constraints for today, constraints for tomorrow. Typically, constraints for tomorrow will include today's variables, because whatever you do today will affect tomorrow. And finally, to create an objective, because we're going to be maximizing or minimizing the expected value of our overall objective, you're going to create some expectation calculation to combine the objectives of the tomorrow problems and the objective of today's problem. Great. So that's the general idea. Again, go watch that video if you haven't done so yet. Let's look at a specific story, a concrete example of this. Here we go. There's a 3-day business of healthcare conference being held at the Miami Business School, and the organizers want to determine how many of the nearby Wiltmore Hotel's 600 suites to reserve so as to minimize their total costs. So for every suite that they reserve today, the hotel will give them a discounted price of $160 per night. Right? Now, what is the uncertainty here? The uncertainty is, I am not sure how many people will show up for the conference, but I need to book a number of suites in advance, because doing so saves me money, right? So if I book suites in advance, it's going to cost me $160 per night. However, here's the catch. If I book too many suites and come the conference, I don't use them all, the hotel will ask me to pay the full price. That is, if I had already given them $160, for each suite that I don't use because not enough people came, I'm going to have to give them an extra $52 to bring this $160 to the full price of $212. So this is one thing that can happen. I can overbook. The other thing that can happen is I can underbook. Maybe I was too cautious and I only called the Wiltmore and booked, let's say, 200 suites, but 300 people showed up. If that's the case, I have to find a place to put these extra 100 people because the Wiltmore will be booked. That's the expectation because they are always, always have high demand. And what the story says is, if there are more conference attendees than there are reserved suites, and again, assume the Wiltmore will be booked, the organizer will have to pay $250 per person per day, because that means they have to send these people to the next closest but not as posh Seneca hotel for $170 a day, plus some transportation costs back and forth from Seneca to the conference site. That's another 80, so 170 plus 80, 250 per day. Okay, so suites that are overbooked are gonna cost me an extra 52 on top of the discounted price. Suites that are underbooked are gonna cost me 250 because I need to place those people somewhere. So the question now is, what should I do in terms of how many suites should I call the hotel and say, I'd like to reserve this many, right? This is my today decision. That's what I have to do now before I know what's going to happen in the future. And the uncertainty here again is how many people will show up. Based on, for example, it could be historical data of holding similar conferences in similar situations. We foresee 6 potential scenarios, aka 6 potential tomorrows. And for each of them, I have a chance of occurrence. Again, this could be based on historical information. And what this table is giving me is the following. We believe there's a 10% chance 300 people will show up, which means I will need this many rooms. There is a 20% chance 400 people will show up, and etc. Okay, so what I want to do is find the best number of suites to book today, considering that I can have 6 potential tomorrows, each of them with these probabilities. And depending on what I do today and what happens tomorrow, there's going to be a higher or lower cost. And I want to minimize the expected value of this cost. All right, so this is the problem I'm concerned with. Great, so if we were to put this into math, following that framework, there's a today decision, which is, I'm going to call this R, number of rooms to reserve in advance, right, with the Wiltmore. This is my stage 1, my today variable. Based on the value of R and the demand in a scenario, right, I can tell you once my tomorrow materialize, and if I know R, because R was my yesterday decision, if I am now in tomorrow, once I know R and the number of people who showed up, I can tell easily, did I overbook or did I underbook, right? And depending on whether I overbooked or underbooked, there is an added cost besides the original cost of pre-booking suites. And the way to calculate this, how many did I overbook and how many did I underbook, is to use the same trick that we used in the goal programming example that we saw together. And if you haven't watched that, I'm going to put a link to that also here in the description of this video, plus up top for you to click on. But briefly, the idea is this. If I know R because I made that decision yesterday, and today I found myself in scenario 1, which was demand 300, right? 300 people showed up. To determine whether or not there was an overage or an underage, right? I overbooked or underbooked, I simply use this trick here with the O and U variables, right? For example, if R is 400, there was an overbooking, right? So this O variable, for this whole formula to work, if R was 400, the O needs to be 100, because 400 minus 100 will equal 300, and U will be 0, meaning I did not underbook, right? If R was too low, let's say if R was 100, well, for this formula to work, this 100 is too low. It needs to come to 300. So the O is going to be 0, and the U will be 200, because 100 minus 0 plus 200 equals 300. So the U will capture if you were under, by how much were you under, and the O will capture if you were over this target of 300, by how much were you over. And this is the trick that we saw together in the goal programming video. If you don't remember, or if you haven't seen that, just go watch the first few minutes of that video and I explain this a little more slowly. But that's the trick that will allow us to capture the over-under in each scenario. Now, as we mentioned before, R is stage 1 variable. There is also a stage 1 constraint, which is, well, the will tomorrow only has 600 suites, so the most I can do is book all of them. So R is at the most 600. And for each scenario, I'm going to have one constraint. So this one constraint here is the constraint for scenario 1 in stage 2. That is to say, capture the over-under if the demand was 300 people. For scenario 2, I also have to capture the over-under in case the demand was 400 people. Notice that the O, I have not a single O, I have 6 of them, because depending on the scenario I am facing, I will have different overages. Likewise, for the underages, I need one of them per scenario. So each of these 6 formulas here are the constraints of each of the 6 scenarios. Now, how do we make the objective function, which I mentioned is that expectation calculation? Well, it goes like this. Forget about this 3 here for now. The today cost, right? The cost that happens no matter what tomorrow is essentially how many suites did you pre-book, the number R, times 160 per suite. Now the expectation calculation goes like this. Remember, if we overbook, right? Each one we overbook is going to cost us an extra $52 because the full cost of the room is $212 and we already paid the hotel $160. So I need to add an extra $52 to get to the $212. So O, every overbooked suite cost me $52. And if I booked too few, the $250 per person that I have to send to the other hotel plus transportation. So if I underbooked in scenario 1, every suite underbooked costs $250. Now, this is going to happen to me only 10% of the time because that's the chance that I will find myself in scenario 1. And then I repeat this idea 5 more times, right? If I find myself in scenario 2, there's an overbooking potential and an underbooking potential. If I overbooked, 52 per overbooked suite. If I underbook, 250 per underbooked suite. And the chance I will find myself in this scenario is 20%, so multiply by that. And repeat for every scenario. So this is the expected expense, right, of the organizers of this conference in terms of the hotel reservation. Why am I multiplying all of this by the number 3? It's simply because this is for 1 day, and they say it's a 3-day conference. So if you really want to be strict here, your overall cost is 3 times this whole amount. That's why I have the 3 there. All right, great. So let's go ahead and put this into Excel and see what happens. Here we are. So we have our today variable, the R variable, right? I can reserve up to 600 suites. Discounted price, full price, and the cost of the other hotel. This is my, this block of gray cells here are my 6 overage variables, the O's, and my 6 underage variables, the U's. Remember that I have to calculate the following expression for every scenario, R minus O plus U, right? To make that equal to the scenario's demand. So I'm going to calculate that here. Here's my R. Notice the R is constant across scenarios. Why is that? Why don't I have several R's? Well, because R is a decision of today, which when I find myself in the tomorrow moment, the today decision is now a yesterday decision, and I can't modify it, right? So whatever I did yesterday is fixed and constant throughout every scenario. That's why it's the same R decision affecting every scenario equally. Great. which means in here I'm going to anchor this B3 because it's the same across scenarios, minus overage plus underage, like in the PDF with the math there that we just saw. And this I can copy through every scenario here to get those 6 expressions. Great. For the expected cost, we're going to have the following. Remember, it's 160R plus, now let's look at this a little bit of algebra here. Notice that 52 is the same, right? No matter what scenario. So every O variable gets multiplied by the probability of its scenario, right? O2 times 20%, O3 25, etc. And they also all get multiplied by 52. So you could go here and do the following. First of all, let me add the constant today cost with the 160 times R. Plus, I can put that 52 in front, and essentially now I have every O variable times its corresponding probability, right? And this I could do with a sum product. Take the probability of each scenario times the O variable of every scenario. And you'll see that this is exactly what that formula we just looked at is doing. And a similar thing happens with the underage variables, right? It's 250 for each of them, and I take each underage variable, multiply by the probability of that scenario. I can do that again with a sum product. Probability times the underage. Okay, so just to bring that back here one more time, right? The today cost, 160 times R, plus the expected tomorrow cost of overages and expected tomorrow cost of underages. And remember that we have the 3-day conference, so I'm going to put a 3 times all of this like that. Great. So we are now ready to go inside the solver. Let's do that. Data solver here. So this is a cost problem, so we're going to be minimizing, right? And the objective formula is in cell B18, the expected cost. I'm going to click min to minimize that. And our variables are the today decision, the R variable, and also this block here of OU variables. Remember, on Windows, I could click the first cell here, press a comma, and then select this other block. On the Mac, you can click here, hold down the command key, and then select this other block, and then hit enter. Okay. And then constraint-wise, we have to do today's constraint is essentially what you book, is at the most how many suites are available. And tomorrow's constraints are 1 per scenario in this case, and they just say the R plus O minus U, right? They have to equal the demands, or aka number of people showing up in each scenario, like we have here, right? These 6 guys, these six equal signs. And the last change is to, well, first make sure that all variables are non-negative. And this is all a linear problem, so it's simplex linear programming solver. And that should do it. Let's take a look. Great. So let's see what this is telling us. It's saying the following. Of course, there is no one today decision that will be good no matter what scenario, right? Depending on the scenario that's coming up, you will be either under or overbooked. But what I want to accomplish is, if I am in the business of running conferences like this, what is the type of decision that I need to make today so that in terms of expectation or long run average, I am doing the best possible? And they're saying, under these circumstances here, the best thing to do is to call the Wiltmore today and book 400 suites. What's going to happen? Well, 20% of the time you will be in scenario 2 and you'll have no overage and no underage. 10% of the time, you'll be in scenario 1 and you'll have overbooked 100 suites, in which case you have to pay the hotel the extra amount to cover the full cost of the room. And the rest of the time, 70% of the time, you will have underbooked, right? In which case, you will have to send these people to the other hotel and pay the $250. But choosing the 400 here minimizes your expected cost, which turned out to be, over the course of 3 days, $306,060. Notice that the best thing to do was not to pick the most likely scenario number, which was 500, right? So that this is not always going to be like that. And if you find that counterintuitive, it's just because the problem is not that simple. There are many things to be taken into account here. So the best thing to do was to choose the 400 here. All right. So this was our first example of a problem of this sort. I hope it helps you understand the concept of stage 1 and stage 2 variables, stage 1 and stage 2 constraints, the expectation calculation for the objective, and all of that. We're going to do one more example of this type to help solidify these concepts. So I hope to see you guys for that video as well. Thank you for watching. Bye-bye.